Hey AP Calculus students, this is a video that has the solutions for your Chapter 8 review, and my name is Mr. McGrath. The first one here, it's I guess you can kind of say that it's a trick question, but it's here at the beginning to make you think about how you decide when you run into a problem like any of these where you have to find an antiderivative about what you should be thinking about. What's the process? What are the different options that you have? So I'm just going to put this aside for a second and give you sort of an outline of how you might think about what the different options that you have are. So you might think first, when you do an antiderivative, when you're trying to find an antiderivative, the first thing you might consider is does the function that you're looking at, that you're trying to find the antiderivative of, does it match up to some kind of known function? Something that you know the antiderivative of. Antiderivative. And if it doesn't, then you might consider, the first thing you would consider after that is, can you do a u-substitution? And that would be something that we covered in Chapter 6. But, just because we're in Chapter 8 now, it doesn't mean that's off the table. So is it just like a u-substitution problem? And then finally 3, if it's not, if u-substitution isn't going to work, then at that point you would consider doing integration by parts. And we might just remind ourselves that that's like Liate kind of protocol there. Or is it maybe a partial fraction decomposition problem? And sometimes, if you're in a particular state of mind and you consider these things first and they don't work, then you might work your way backwards through the list. But I think that this is probably generally the order that you want to think about things in. So considering that, let's look back at this first problem here. So here's our antiderivative. So maybe you're really like deep into the mindset of Chapter 8. Like, okay, is this an integration by parts? Well, integration by parts, those are things that look more like products. Like this looks like integration by parts, and so does this. In fact, that's like algebraic and trig, so maybe this one would be good for tabular integration. This one doesn't look like either one of those. It looks maybe at very first glance like it could be partial fractions, but 2 plus x squared, that doesn't factor, so that's not going to do anything for us there. And it's definitely not integration by parts. So then that means we have to try to either do u-substitution or match it up to something that we know. U-substitution, if this was going to yield to that method, then the u would have to be the bottom of this, and the du would be 2x, right, the derivative of the bottom, and I don't have an x on the top. If this was 3x on the top, then I could do that. But it's not. So that's not going to work either. So then we're back up to number 1. Does this match up, or is it close to matching up to something that we know? And it is. It's kind of like the derivative of tangent inverse. So our thought bubble is, well, if I could get this to match up to 1 over 1 plus u squared, then would be in business. So the problem here is, well, there's a couple problems. First of all, there's a 3 there, and I'd like that to be a 1, so that's easy enough. I can just move the 3 to the outside. And the second problem is that if you're going to try to get it to match up to this 1 here is not negotiable. That has to be a 1 there. So I'm going to factor a 2 off the bottom of this. So factoring a 2 off the bottom, I'll bring that all the way to the outside. And if I factor a 2 off this, that leaves a 1 here. And if I factor a 2 out of this, well, there wasn't a 2 there to start with, so dividing a 2 out is going to leave that as x squared over 2. I'll give you a second to look at that. Now, if I would like this to match up to this, then that's going to have to be the u squared. So u squared is going to have to turn into x squared over 2, or maybe it's better to say that the other way around, that x squared over 2 is going to have to turn into the u squared. So if u squared has to be x squared over 2, that means u has to be the square root of 2 over 2 times x. Right, that's square rooting that. That's x over the square root of 2. That's the same as this. And then that means that du would be the square root of 2 over 2 times dx. So that means that in this here, if I want to make that substitution, I'm going to need a square root of 2 over 2 on the inside, which means on the outside, I will need the upside down of that. I'll need a 2 over square root of 2, so that everything cancels out. And 2 over the square root of 2 is just equal to 2. Sorry, that's not true. 2 over the square root of 2 is just equal to the square root of 2. You can rationalize that. And it doesn't matter if you do or you don't. But if you do, that's what it's equal to. So let's see what this all turns into now. So on the outside here, those 2's would cancel out. I'd get 3 over the square root of 2 there, or if you use the square root of 2, it could be 3 square roots of 2 over 2. That would be fine there also, either way, times the integral. Now I've got 1 over 1 plus u squared. That was my goal. And that 2, not u, u2. This is tangent inverse u plus c. So we're done here, except that this problem was written in terms of x's, so it would be more correct to finish this by saying that, let's see, u is equal to the square root of 2 over 2 times x. So there you go. That's how you do the first one. So it's not really a Chapter 8 problem, but I put that there first for you to think about. What are the different kinds of, what are the different methods that we have at this point for evaluating antiderivatives? Alright, now this definitely looks like integration by parts. So I will do my u dv. It's not a tabular integration problem because this is not, it's not algebraic and trig or exponential, it's inverse trig. So let's choose the u and the dv. So using my LIATE acronym, I have inverse trig and algebraic. So inverse trig should be first. That's the thing that I should choose for the u. So that would be tangent inverse of x. And algebraic, that's my x. That should be here. And try not to forget the dx there. Okay, so let's see, du, the derivative of this, well, we're all warmed up for that. That's 1 over 1 plus x squared dx. And the v, the antiderivative of that is x squared over 2. Alright, so that's fine and good as long as you remember what the recipe is for integration by parts. So this integral that we excuse me, described as u dv, that can be rewritten as u times v. So I'm going to write that as x squared over 2 times tangent inverse x minus the integral of v du. So v du, that's x squared over 1 plus x squared. And then there's a 1/2 there. I'm going to put that on the outside because that's just a constant. Dx. Okay, so we've made some progress, but here still I have something that I need to figure out how to do that. And the problem here, it's not a partial fraction problem because I can't factor the bottom, the 1 plus x squared, that doesn't factor. And I have the same degree on the top and the bottom. So I think I need to do a quick long division here to figure out what's going on here so I can rewrite that. And I think at this point maybe I'm going to move to a separate sheet here and just try to deal with that. So I'm trying to evaluate this part of the problem. So I'm trying to figure out how many, maybe I'll write this like this now, x squared plus 1, how's that going to x squared? So, well, that's, if I multiply by 1 there, that'll line up, right? And if I subtract that, I just get a remainder of -1. So that means that x squared over x squared plus 1, or 1 plus x squared, is equal to 1 minus the remainder over the divisor. So that means I can rewrite my integral. Instead of this, I can write it as the integral of 1 minus the integral of 1 over, and maybe at this point I'll write it like that. Looks a little bit more familiar like my tangent inverse. And the antiderivative of 1 is x, minus the antiderivative of this is tangent inverse x. So that means here I've got x squared over 2 times tangent inverse x minus 1/2 times, and then here we decided that that's equal to x minus tangent inverse x. X minus tangent inverse of x plus c. And I would be okay in a free response kind of situation if you left it like this. There's a little bit of simplifying that could possibly be done because there's a tangent inverse here and another one here. So you could distribute this and factor the tangent inverse out and deal with all that. But I'll let you do that if you want. You can check with me if you've got a version of that answer that you've simplified and you want to make sure that it's correct. But there you go. That's, on a scale of 1 to 5, say, for integration by parts, that's probably a 4. That's fairly difficult, I think, because even once we did integration by parts, we still had an integral here that we needed to do more work with. All right, number 3. This one should be a piece of cake after that, because this one we can do tabular integration. So I've got x squared, and I've got sine of 3x. So taking derivatives here till I get 0, and then taking antiderivatives. So be very careful here. The antiderivative of sine is negative cosine of 3x. And since there's a 3 in here, I need a 1/3 on the outside. The antiderivative of cosine is positive sine. So we get that. And another 3 is going to come out on the bottom there. And then finally, the antiderivative of sine is negative cosine, so the negatives will cancel out. Another 3 comes out. And that's how that works. And don't forget that every other one of these arrows we start with positive, but then every other one we get an extra negative sign in there. So my final answer here, I'm going to have x squared times this. So there's a negative sign, negative 1/3 x squared times the cosine of 3x. And then here I've got two negative signs, those cancel out. So positive 2/9 times x times the sine of 3x. And here I've got just positives plus 2/27 times the cosine of 3x plus c. And that's how you do that. So definitely, I mean, it's a messy looking answer, but the process is not difficult to get that. You just have to be very careful, especially, I think, taking the antiderivatives here. Make sure that you're comfortable doing that, the way that these factors here, if there's a multiple on that x, how those come out on the bottom. All right. Here, this looks like it's got the potential to be partial fractions. That bottom of this would factor, but I have on the top here, I've got the same degree, so I'm going to have to do long division here first. So x squared minus 9, how many times does that go into x squared minus 8? Well, if I multiply by 1, that'll get the x squareds to cancel. So negative 8 plus 9 gives me a remainder of 1. So that means this integral, that x squared minus 8 over x squared minus 9 is equal to 1 minus, plus, remainder was positive there, plus 1 over x squared minus 9. Okay, so I'm going to do the same thing that I did before. I'm just going to move over to a separate sheet here to evaluate this part of this integral. Of course, the antiderivative of 1 is just x. Oops, there's another piece of this. All right, so I need to evaluate here. I need to figure out how to do partial fractions with this. So let's see, it's going to be a over x plus 3 plus b over x minus 3. So that's a x minus 3a plus bx plus 3b all over the common denominator. So that means that this has to match up with this. Now there's no x's there, so that means the coefficients of my x's, that a plus b must equal 0. And my constant term is 1 here, so my constants here, that's minus 3a plus 3b is equal to 1. So if I multiply this top equation by 3 so that I can do elimination, then I get those cancel. I get 6b is equal to 1, so b is equal to 1/6, so a must be equal to negative 1/6. Which means that this, I'm going to switch. I like to put the positive one first. So b, that means 1/6 times 1 over x minus 3. I'm putting that one first because it's positive, minus 1/6 times 1 over x plus 3. Okay, so let's move that back to our answer here. So this, I haven't evaluated any, I haven't done any antiderivatizing yet. So that's 1/6 times 1 over, which one was first? This is the x minus 3, I think. Yeah. The x minus 3 minus 1/6 times 1 over x plus 3. So the antiderivative of 1 is x. The antiderivative, that's 1/6 times the natural log of x minus 3 minus 1/6 times the natural log of x plus 3 plus c. and that's all fine and good. That is the answer. It's correct. But you could, since these have the same coefficient in front of them, you could write that as, factor that 1/6 out, and that's the natural log of, since this is subtraction, that would turn into x minus 3 over x plus 3. There you go. Just so you know, and you have experience with this now too, with the practice multiple choice questions that I gave you. It's more typical for College Board type problems for us to get things that are just like this. In other words, things where you don't necessarily have to do long division first. But since we did have to do that first, that's why we're getting this quotient here and that other piece of the antiderivative. All right, number 5. Here, this looks like it's got the potential to be partial fractions if I can factor the bottom here, and I've got a degree in the top, 1 less than the bottom, so that's good. Let's see if we can factor the bottom of this. So the two factors would have to multiply together to be 14. So it looks like that's going to be 2 and 7. And I'm getting a minus 5 in the middle, so the minus 7 plus 2, oops, sorry, minus 7 plus 2, that's what's going to give me that. Okay, so that means this is going to decompose into a over x plus 2 plus b over x minus 7. So that's ax minus 7a plus bx plus 2b all over the common denominator. I'm just not writing that out again, we know that it's that. So that means that if we look at the top here, the a plus b, the coefficients of the x's, well, the coefficients of the x's must be combining to give us 2. So a plus b must be equal to 2. And then on the for the constant term, that's coming from these. So minus 7x plus 2b must be equal to 31. So I'm going to take the top equation to get this to do elimination. I'm going to multiply that by negative 2 times negative 2. And if I do that, that gives me negative 2x minus, negative 2, why did I write an x there? This is to be an a. So minus 2a minus 2b, that's what I'm setting that up for, and minus 4. So that's minus 9a, and then the b's cancel out, and I get 27 here. So it looks like a is equal to negative 3. If a is negative 3, then b must be 5 for those to add up to 2. Okay, same as I did in the last problem, I like to write it with a positive term first. So after doing our partial fraction decomposition, this original integral turns into b, which is 5 times, sorry, I was going to write 1/5 there. I'm in the habit of writing those fractions, but this time it just came out to be 5 times 1 over x minus 7. And then the a coefficient, that was negative, minus 3 times 1 over x plus 2 dx. So the antiderivative of this is 5 natural log x minus 7 minus 3 natural log x plus 2. And because these coefficients are not the same, I can't factor that out. So do you simplify this? Well, I mean, you could bring these in as exponents and then do that. So you could simplify this to natural log of x minus 7, you could put this all in one big absolute value signs if you wanted to the 5th over x plus 2 to the 3rd plus c. You could simplify it to that, but oftentimes in my experience the aesthetic seems to be when these are different coefficients that you don't necessarily need to do that. But you could, because there is a logarithm rule that says we can bring these coefficients in as exponents. So either one of those is fine. All right. So what about this? This looks like integration by parts. I've got an algebraic and an exponential, so that's actually good for tabular integration. The difference here is we have a definite integral. So let's set that up. X e to the x, derivatives here until we get 0, antiderivatives here. That's easy. Until we get, well, until we reach the end of the table. Don't forget that the sign flip happens there, every other arrow. So the antiderivative of this is x e to the x minus 1 e to the x. And I'm actually going to evaluate this in this case because it's a definite integral. So we'll plug in the natural log of 8. So that's natural log 8. And then what's e to the natural log 8? Well, the exponential function and the natural log function are inverses of each other. So if you raise e to the natural log 8, you just get 8. Minus e to the natural log 8, that's another 8 there. Minus, what do I get when I plug in 0? Don't just assume that you get 0. We do get 0 for this piece. Minus e to the 0 is 1. So let's see what we have here. Simplifying that, I've got natural log 8 times 8, and then I've got minus 8 plus 1. There you go. Number 7, well, it's not partial fractions because that bottom's under a square root sign, and it's not integration by parts because it's not a product. It's not a liate kind of thing. So what to do with that? Well, this actually looks kind of like it could be this. In other words, it could match up to sine inverse, the derivative of sine inverse. So let's see if we can make that happen. So this is another kind of fake out problem here, kind of like number 1. So just like tangent inverse, this 1 right here, that's non-negotiable. So I need to factor this 16 out of there. Now, if I factor the 16 out, when 16 factors out of this, it will actually be a 4 because this is inside a square root sign. So a 4 comes out there. I'm also going to move that 5 out off the top because I'd like that to just be a 1. Right, so we've got 1 over, I factored the 16 out, that came out as a 4 on the bottom. Now I have to factor a 16 out of this, and there wasn't one there, so that's going to have to be that. So that means u squared needs to match up to x squared over 16. So u is equal to x over 4. And here, I have not changed anything here yet. All right, so let's see what we have now. On the inside here, I've done what I needed to do to get this to look like sine inverse. Now, what will my limits of integration be? To find those, I need to take my x numbers and turn them into u numbers. So 0 divided by 4 gives me still 0, and 4 divided by 4 gives me 1. So that's 5/4. The antiderivative of this is sine inverse of u from 0 to 1. So that's 5/4 times the sine inverse of 1. So what angle do you take the sine of to get 1? And make sure that you're in the right little restricted domain between negative pi over 2 and pi over 2. So if you want to get 1, that would have to be pi over 2. And then what angle do you take the sine of to get 0? Well, it's just 0. So 5 pi over 8 is the answer there. All right. How about these improper integrals now? So improper integrals, there's two different ways. So sometimes this is one way of writing this. I wrote these problems in this way because sometimes our buddies over at the College Board like to write improper integrals in this way. So the limit as b approaches 2 of this integral just means the same thing. That's what we've been doing. I mean, what do you do when you evaluate a limit? You plug that number in, right? So it means the same as this. And I mean, this says right here that it's an improper integral. It doesn't have the infinity like this one does, for example. So why is this improper? How would we know that? Well, 2, if you plug 2 in here, that's right up against a vertical asymptote. So that's trouble. So let's see what happens here. That doesn't change how we do it. We just have to watch out for those infinities when we evaluate our integral here. So let's see. What's the antiderivative of this? Well, the antiderivative of 5 is 2 minus x. This is just an x to the first power, so this is a natural log. I'm going to move the 5 to the outside, and here that's going to be a natural log absolute value of 2 minus x, but since it's not just a plain old x there, I have to divide by the coefficient of this. So that's like dividing by -1. So that's going to give me a negative sign on the outside. And boy, is that easy to forget that. And that's my antiderivative. So I need to evaluate this from 0 to 2. So what does that give me? It gives me -5. Natural log of 2 minus 2 is 0. And then minus -5 times the natural log of 2. Now this is a bust because the natural log of 0, if we're thinking in terms of limits, which we always are, then the natural log of 0, what that's really trying to do, remember what the natural log function looks like? As x approaches 0, this plunges down to -infinity. So I've got -infinity minus or plus whatever, some other thing. So this is divergent. So sorry, no answer, just divergent. All right, how about this? So let's see, again, this is just the same as b approaches infinity, so our book, we might have seen this written like this. It's the same thing. Now, how do we find the antiderivative of this? Thinking about the different techniques that we have. First thing you consider, is it just a thing that I know? No. Will u-substitution work? Well, u-substitution, you would always consider a thing that looks like the what's inside to be your u. That'd be your first option. And if my u was 1 plus x squared, then the d would be 2x, and that looks like it's going to work because I've got the x there. So if u is equal to 1 plus x squared, du would be 2x dx. So that means I'm looking good here. I would need a 2 here, which means I would need a 1/2 on the outside. So this would turn into 1/2 times the integral. Got to adjust my numbers here, make them into u numbers. So u is equal to 1 plus x squared. So that's going to be 2 there. And then 1 plus infinity squared, that's still infinity. And then on the inside, my 2x dx got all taken care of there. And on the bottom, I have u squared, and actually, I'm not going to write it like that. I'm going to write that as u to the negative 2 du. That's better for calculus. So, got 1/2, and then it's the antiderivative of u to the negative 2. So, reverse power rule, I bump the exponent up by 1, and then I divide by the new exponent, dividing by negative 1. It's just like introducing a negative sign there from 2 to infinity. So this is looking good because infinity to the negative 1, that's 1 over infinity, and that goes to 0, right? 1 over infinity is 0. That's how these things generally give us answers, is by ending up with 1 over infinities. And then minus, when I plug 2 in that, I get 1/2. So if that's 0, I get negative 1/2 times negative 1/2. That's positive 1/4. All right, last one. So here, this looks pretty good, except if that was just u to the 2/3, I'd be okay. And remember that this is the same as the integral from 1 to 2. Why is this an improper integral? Well, if you plug 2 in, you get 1 over, that's a 0 on the bottom, so that's the problem there. So in our book, this problem would have probably been written like this. And here's a challenge for you, or something to think about. There was a problem, I think it was the step-by-step number 14, part A, that had you think about what power here, like what does this power have to be for us to get an answer for an improper integral, and what powers here end up being divergent. So if you remember the result from that, that might tell you something about this problem, whether we're expecting to get an answer or whether we're expecting to get divergent. I'll let you think about it. Wouldn't be a terrible idea to pause, maybe look back at that problem and think about this. Really good thing to try to understand better than just marching through the procedure here. Okay, so I need to u-substitute this so I can get this into workable form. So u is just going to be equal to x minus 2, so du is just equal to dx. It's a straight swap, but it gets me that as u to the negative 2/3. I didn't have to import any numbers or anything there. du. So now my u numbers are going to be different. So x minus 2, so let's see, that's 1 minus 2, that'd be negative 1 there, and then 2 minus 2 is 0. Okay. What's the antiderivative of u to the negative 2/3? Well, to take antiderivatives, you bump the exponent up by 1, and then you divide by the new exponent. So dividing by 1/3 is the same as multiplying by 3. Right. From negative 1 to 0. So let's see if we get an answer here. So I got 3 times, this is looking pretty good. I don't have any infinities here, there's nothing on the bottom, so like when this was less than 1, or between 0 and negative 1, say, taking the antiderivative bumped it to positive, and that's going to give us an answer here. So I've got u 0 to the 1/3, which is 0, minus negative 1 to the 1/3. The cube root of negative 1 is negative 1. So 0 minus negative 1, that's 1, times 3 is 3. And that's your answer there. And I'll leave the bonus for you to try. It's kind of a crazy problem, the bonus, and I think I made that problem up in one year that I gave a problem similar to that. The numbers did not work out to be nice, and I hope I fixed it. And it's something that does. But you can try that, and if you did try it and you want to see if you got the right answer, then ask me and we can check it out.